Okay, people still joining, but we will get started. Welcome, everyone. My name is Mark Dillon. I'm the Chief Technical Officer of Basemark, and this is a webinar of Introduction to the Basemark Automotive Test Suite, or BATS. One of the things that makes BATS very special compared to many other benchmarks on the market is it is the only benchmark that is tailored for automotive and embedded applications. And today we're going to take you through many of the features and benefits of BATS for automotive development on embedded platforms. First, a few words about Basemark. Basemark has a long history in automotive development in both products and services. We have worked with OEMs and Tier 1 companies all over the globe with many successful projects behind in our belt. Our customers have been some of the biggest OEMs and Tier 1s in the world, and we have done work on instrument clusters, on autonomous drive, AR, heads-up development, or heads-up displays, and lots of other work in these products and services areas. Many of our customers that we can mention are semiconductor companies, where semiconductor companies are using our benchmarks in order to understand how those semiconductors that they are developing compare with other companies, compare with competition. They use BATS as a reference workload in order to understand what type of automotive workloads will run on a given SoC, and then be able to compare that with their new development and with what competitor offerings are. We also have many customers, unfortunately, under NDA that we cannot mention here today. But if you would like to hear more about those, then please schedule a sales call with our salespeople. And there will be information about that at the end of the webinar. We also have a host of certifications and are able to produce safety-critical work in both our products and services departments. And we have fresh TSOX 9001 ISO and 27001 ISO certifications. Basemark's long experience in automotive development and development on embedded systems gives us an advantage for our customers to be able to help them understand how to optimize, how to create requirements that can be implemented, and how to be able to achieve time to market in a very difficult development environment. By using BATS, a OEM can understand how to dimension a system, how to understand how to put workloads onto a given SoC that maximize that SoC's capabilities, as well as understand the correct level of SoC performance that's required for a given task. We've worked, once again, with leading OEMs and Tier 1 suppliers, developing autonomous drive L4 and L5 systems as well, in-cockpit instrument clusters, as well as in-vehicle infotainment. So Basemark's expertise on small footprint, high-performance software, and benchmarking and system dimensioning are things that we're here to talk about today. I will hand over to Damian Nachman after this slide, who is the project manager for BATS. We can see a small snapshot of BATS in the upper left corner, which is one of the instrument clusters that we've developed. We're also doing a lot of this kind of work in our professional services department. On the right, we have a description of many of the different functional areas that Basemark has experience in and expertise. Everything from doing machine vision, sensor fusion, neural networks, inference engines, classifiers, instrument clusters, in-vehicle infotainment, and all of the things that are required for autonomous drive. We also have our rock-solid engine, which our benchmarks are built on, and which is also a separate product that is optimized for graphics and compute in embedded systems and automotive. These will work in conjunction with whatever operating system or SoCs that you choose and whatever device drivers that you choose. In order to choose the right device driver, Basemark Automotive Test Suite, or BATS, helps you understand what types of workloads will work on what type of operating system for what SoC in combinations that then can be used to understand what SoC to purchase and what type of requirements to put into your software development in order to achieve the right result at the right time and a good time to market. So I'll now hand over to Damian Nachman, who is the product owner for Basemark Automotive Test Suite.
Yes, thank you, Mark. Thank you very much. So first introduction, I'm Damian, project manager for BATS and also technical artist here at Basemark. Basically, like Mark said, we developed BATS to basically make a realistic benchmark for automotive using our experience working with OEMs, implementing HMI, and also working with SoCs who actually develop these platforms to make the most realistic benchmark for automotive use cases. We achieve that by offering a collection of graphics tests and computer vision tests that can be combined, tailored, and configured to basically match a lot of different automotive use cases. The difference between classic graphics benchmarks like we offer in the past is that those use mostly gaming realistic workloads that usually utilize large amounts of light sources, very complex lit shaders, high amount of geometry, things like that. Instead, with BATS, we focus on the rendering features that are relevant for automotive HMI that we often use to implement automotive HMI. Stuff like very large amount of custom effects shaders, for example, a lot of render targets, render layers that each can have its own post-effect shaders. It's a very common use case in automotive to layer the UI, which have a big impact on performance. Also deforming, basically vertex deformation along road curves, things like that we try to emphasize on to give a more realistic workload. The benefit of that is that both OEMs and SoCs can benefit from that. Specifically for SoCs, they can evaluate their platforms, their drivers' implementations, understand limitations, bottlenecks of the device, understand the performance of their device and their competitors' devices. And for OEMs, it is used to select the appropriate SoC, the appropriate automotive platform, and also help in accelerating the HMI development process. So that's in a nutshell. Now I will basically go and show how BATS is used, show the various graphics tests and computer vision tests, and show more detail how everything works. So moving forward, starting with the Orchestrator. With BATS, we have the Orchestrator, which is the front-end tool, which is used to select the tests, combine them and configure them however you want, set up the remote connection on your for your remote devices via SSH, run the tests, and then visualize the results using the visualizer to analyze the results, performance metrics, and workload complexity. So there's that. And basically how it works, very simple. With Orchestrator, we select the tests, configure each test. We support large range of graphics APIs, which you can choose from. Choose the device, the display, set up the remote connection, and then launch the tests and get the results back and analyze them. And now I basically just want to briefly kind of show a little demo of how we use the Orchestrator in our Windows demo, for example. So I will actually share screen. Take me a minute. So hopefully you can see my screen, and hopefully you can see Orchestrator on my screen. I believe you can. So how that works, we first select the test. For now, I'll select the IVI test. We have different configurations. In the final version, we'll have a lot more. This is an initial version. There's more updated versions also with more configurations that we will deliver soon. So I'll choose to run one time, leave everything as is for now, and add the test. You can see that in the settings, I can choose my graphics API and such. This will be actually available per test. And I will basically, this time I will just run locally, but you can also use a SSH connection. And I will execute the test. And at this point, it will run locally on my machine. So we have the IVI. And this is the development build. And you can see we have, for example, systems check sequence where we use our matcap shading on our vehicle with reflections and all these dynamic text rendering, custom effect shaders. So this is the systems check sequence. And again, keep in mind, this is development build. The IVI specifically will have two configurations, low and high, two LODs in essence, levels of detail, with different rendering features. Low end will be less complex, high end will be more complex using lit PBR shaders and vertex deformation along Bezier curves for road curves. Here's the Park Assist that will actually use that feature. Also, the background actually, right now it's video streaming, but we will actually do dynamic. Actually, we will use the video stitching test we have to dynamically stitch a 360 video. So that was the IVI running. I will now click Show Results. This is a very early version of the results visualizer, but we can see the results over each frame. You'll be able to click and have a tooltip that also shows you per frame the workload complexity, what is actually rendering, and how it affects performance. So you can analyze the results from your JSON results file, but also compare different results files. And you will have a lot of different metrics you can visualize, not just frame time. So going back to the presentation, this is the orchestrator and how it's used. Very simple. I will now go into the graphics tests, what each of them are actually, what they actually mean and what they actually contain. So graphics tests. Again, as I mentioned before, we're making graphics tests that are actually reference implementations, optimized production-ready implementations for automotive HMI. We offer entry-level cluster test, premium-level cluster tests, which are separated into a driver assistance module and an autonomous module, are medium intensity and high intensity. Each of those correspond to. In-vehicle infotainment, which I just showed you, which can be combined with all of those and configured for low or high-end setting. AR test, which is planned for 2.0, so an AR workload for augmenting ADAS visualizations on top of a video feed or projected onto a HUD. And a separate navigation test that we will take localization data and procedurally generate the 3D navigation environment and the road curves and all that stuff. And support graphics APIs, support a wide range of graphics APIs, GLES 3.1 currently, planning to support 3.2 as well. OpenGLES SC, which is actually GLES 2.0. Vulkan 1.0 will support Vulkan 1.1, and also we'll hope to support Vulkan SC. Of course, that is not yet available publicly. When it does, we will actually support it as well. So starting with the entry-level cluster test. This is the most basic test we offer. This represents a classic instrument cluster design, mostly 2D in essence. Of course, everything is implemented in 3D as it's running in a real-time 3D engine. Basically, your classic instrument cluster test. Speed, gauges, telltales, menus, ADAS, 2D ADAS visualization, systems check, turn-by-turn navigation. And this is our most basic test, which is targeted for very low-end devices such as IMX6 and the like. Then we have the premium instrument cluster test, the driving module specifically, which is the mid-level test. And this is a step up in complexity. In this case, we combine classic cluster elements, like all the gauges, telltales, navigation, and such, but done in a more complex way, and also including on-rails ADAS visualization. Again, this is more complex, using real-time lighting, more complex custom effects, shaders, and such. This is a considerably more complex workloads, also utilizing multiple render layers, each with its own post-effect shader. A common use case for whenever you have to do UI or automotive UI, you have to render all these layers and layer them on top of each other and manipulate them separately, which puts a big effect on the intensity of the workload. And I can actually show a video of that. So again, let me swap my screen share. Just a minute. So I will now show how the entry, well, not the premium driver assistance module looks like in a video sequence. So we can see the ADAS on-rails visualization, distance warning, lane keep assist, lane change assist, brake warning, pedestrian crossing visualization. We can see on the side we're also transitioning to media and 3D navigation at the same time. All the text is done with text rendering dynamically. And this is a snippet of that test. Yeah, I will go back to the presentation now. And moving forward. Next up is the premium cluster test, autonomous module, which is the high-end workload. This is the most resource-intensive test we have. And this basically shows a use case of full 3D navigation combined with 3D ADAS visualization. Again, this is a lot more resource-intensive, using real-time lighting, PBR shaders will be used for this. A lot of vertex deformation to basically deform our augmentations, our ADAS visualizations, deform them along the road. Again, a lot of render layers used here, a much higher vertex count than the previous test. This is a lot more resource intensive, and this should stress very well any existing embedded device currently used for automotive. And yes, 3D visualization means we also going to have a POI visualization, a maneuvers visualization on top of all the ADAS features. And this is the premium cluster test. IVI, I showed it previously in the demo, but again, IVI test can be configured low-end or high-end setting, focusing on park assist with 360 video stitching, systems check, navigation, 3D navigation, all the common use cases for IVI. And I will not show the video again because you basically saw the sequence. I will just skip it for now. Not shown here are also the AR and separate navigation test, which I mentioned, which will, again, procedurally generate a 3D navigation environment on top of, well, basically in a separate test focused for this, but also using actual localization data. And this is for BETS 2.0. And I will basically show the performance metrics, what we actually output. We can see here all the classic metrics that are useful to evaluate the device, frame time, average FPS derived from that, startup time, which actually is comprised of asset loading time, shader compilation time, things like that. memory consumption, memory bandwidth, GPU and CPU usage, things like that. We'll also probably add additional metrics on top of that. This is what we currently aim for, but we want to even achieve more. And on top of that, we have workload statistics, scene statistics, basically telling you workload complexity, how complex the workload is, what is actually happening, what is actually rendering. Again, draw calls, draw batches, vertex counts, triangle counts, primitive counts, effects changes, shader switches, compute batches as well, and render target count, render target switches. So you can understand, evaluate the performance of the device, but also understand the complexity of what's going on, and also be able to learn from that. So that's metrics. That's the results in essence that are shown in the visualizer. Then we also have computer vision tests to make our tests more realistic. We can combine computer vision tests with the graphics tests. And the computer vision tests are listed here. We have the core tests implemented in OpenCV using OpenCL. Core tests include histogram, canny edge detector, fast corners, optical flow pyramid, Laplacian image pyramid, mean and standard deviation. We also have the video stitching test, again, implemented in OpenCV using OpenCL, basically doing 360 video stitching. And the ADAS tests planned for 2.0. These will be done with rock-solid compute, mostly for object detection and classification, pedestrian detection, vehicle detection, traffic sign detection, and traffic light detection. And also sensor fusion tests, both extended Kalman filter and convolutional neural network for sensor fusion. And that's it. These are the computer vision tests. Again, can be combined with all the graphics tests to match your own use case, your own either concept requirements or anything really. Get a realistic automotive workload. And that's it. That is all. I will basically now go into use cases and benefits. How to use BETS, what are the benefits for different cases. Both SoC manufacturers and OEMs, how they can use it for their benefits. So firstly, BETS is very useful for platform evaluation, SoC evaluation. So you can evaluate different SoCs, different platforms and configurations, including multiple SoCs, multiple displays and such, across multiple graphics APIs. And again, this is achieved with the library of tests I mentioned before. How this works is simple. You can set up different configurations. On the left, config 1, you can see we have a single SoC. On the right, we have a configuration with 2 SoCs. You can basically evaluate these configurations, understand the performance and bottlenecks, evaluate the drivers implementations, look at the workload complexity to understand what is actually causing the bottlenecks, evaluate the device, and also compare different configurations. So in this case, we use the same workloads, but on different devices. We compare the 2 SoCs, understand which SoC performs better under different scenarios or using the same scenario. And this basically allows OEMs to choose the correct SoC, the correct platform for their use case. Basically get the best value for money or be able to, from the get-go, be able to achieve any requirements that the concept specifies. And for SoCs, this gives them the ability to evaluate their own device, evaluate their drivers implementations, and also compare to the competition devices, see how well they perform. So that's for SoC and platform evaluation. This is very straightforward. Also for HMI development, and this is specifically for OEMs implementing HMI. There can be a lot of benefit from BETS to accelerate HMI development, and I will explain now why. But the idea is to concept and produce your implementation with technical limitations and considerations in mind, and basically reduce production time. And the problem stems from this, the problem that we're actually solving here. And the common approach to HMI development, we've seen this with every OEM we work with. When we help them implement their own HMI, we noticed that the process is usually this. Actually, in all cases, it was this. There was the requirements and concept, which is then developed into an implementation that can be profiled on the target device. During profiling, issues, performance considerations are discovered, and then you need to go back, either rework your implementation, optimize it differently, and sometimes there's no choice. You have to go back to concept. You realize that what you're trying to do is perhaps not possible on the target device for different reasons. You have to go back to the concept and requirements, modify those, and then implement those again, optimize those again, profile again, and again, repeat the process, this iteration loop, which is very time consuming. And we basically can help sort of break that cycle in a sense. Every time you have to implement something for real time and optimize it, it's time consuming. There's a lot of work involved, both design implementation, and development. And these iterations can cost a lot of time. And basically, most OEMs now work in a trial and error sort of way, which is very time consuming and increases production costs. With BATs, the process is as such. As early on in the concept and requirements phase, when you don't have an implementation that you can profile, even at that point, you can use BATs, configure BATs to match your requirements and concept, evaluate the platform, understand technical limitations, bottlenecks, all these considerations, make the necessary changes to the concept early on in the concept phase, approve and lock your concept early on. And for implementation, same thing, you can use the information gathered, limitations, metrics in regards to workload complexity, and choose the correct implementation and optimization techniques and methods. So you actually develop with the target limitations in mind. And at the same time, you can refer to the BATs reference implementations. So the graphics test we offer are also reference implementations that can be studied, analyzed, and understood how we do certain techniques, certain optimizations, learn from those, and apply them in your own project to choose the correct implementation and make the most optimized implementation possible. We have a lot of knowledge gathered from benchmark development and game development, and all these techniques are actually in these reference implementations, and you can learn from them and utilize them for your benefit as well. And in more detail, it basically looks like this. We can see the requirements on the left. In this case, the requirement is having IVI, AR, and IC modules running at the same time on the same device. You can see this is a bunch of requirements here, like resolution, rendering effects. On the IC instrument cluster, you can see there's, for example, a need for vertex deformation and PBR shaders and reflections. Using those, you can actually choose the correct configuration of BATs, which offers, again, a wide range of tests to configure. You set your configuration, evaluate the performance, go back to requirements, modify them early on, or go straight to production using these lessons you learned from evaluating the device and also referencing our implementations. Choose the correct implementation route, methods, techniques. Make the most efficient implementation as possible, as soon as possible, with less iterations, less time spent. And of course, as I mentioned early on before, also you can use BATs to evaluate possible platforms, not just a single SoC, but complex automotive platforms comprised of multiple SoCs, spanning multiple graphics APIs, running on multiple displays. You can test all of those and compare those and choose the correct device for you. And that is all. That is BATs. This is what we we are doing with bats. And that's it. I'm pretty much done. I guess to you, Mark, back to you. Can you hear me, Mark? Oh.
Yep, took a moment for things to wake up. We've taken a handful of questions behind the scenes. I will just highlight a few of them, which is that, a reminder that BATS runs the same workload across different SoCs. And we run on everything from the lowest spec device we have in our lab is IMX6 Dual Lite, I think about a 10-year-old device. And then we have everything up through, advanced Qualcomm, Renesas, Samsung, Heike, lots and lots of different devices. So comparing an SoC means taking a given workload or set of workloads with BATS, configuring those in the orchestrator, and running the same workloads across different SoCs in order to compare their performance, and then be able to understand what type of workloads you will be able to support with what type of SoC, and then be able to choose the right system for the job, and also be able to understand what type of different scene complexities and requirements that you will need to put in to be able to achieve that kind of performance on your own production implementation. There were a couple of other questions that I can touch on, which is that we are, as Damian pointed out, building some advanced AI benchmarking. So yes, you will be able to, in the next version of BATS, be able to benchmark object detection and classification, for example, as Damian was mentioning towards the end of his presentation. So very interesting stuff. I didn't see any further questions, but we have we're a little bit early. If there are any extra questions, we can give you a moment or so to put those into the chat. The orchestrator can handle multiple SoCs. So that is, the orchestrator has a SSH function, which we use for remote call to different devices. So once configuring a device, it is possible to use the orchestrator from a single PC or workstation, and then be able to execute tests on many devices. That can also be done with scripting or with continuous integration, for example, if you want to run BATS workloads as part of your continuous integration, if you're doing driver development, or if you are wanting to run comparisons with other different things. Any other questions? The hardware assumptions for each test. Our BATS customers typically get, as part of an original contract, device of their choice or device family of their choice with an operating system and the adaptation of BATS for that. Most of them just run out of the box by default, because the rock-solid engine provides a cross-platform interface so that the same workloads can run on many different devices and across many different APIs as well. Another thing, question that came up and went was that you are able to test different APIs, different API versions using BATS. So if you are running a production system and get an updated API from the vendor, you are able to independently verify that using our benchmark. And then if there are any performance issues, then you have an independent and portable way to prove that you're having a certain issue with a new version of an existing driver for your production system. I can give one last call for questions if there are any. I think I covered them all. But I would like to thank you all for joining. I would like to thank Damian for the presentation and the enthusiasm, and I look forward to seeing you in another Basemark webinar. I'm Mark Dillon, CTO of Basemark. Thank you for joining.